Okay, so now I'm going to do some of the review, I would suppose we'd call it, of Chapter 5 that we started getting into, just for some of the more important topics that I want you to remember when we move on, starting, I guess, it would be next week. So the first off is gates, right? Basic gates, and gate. Nice flat line, dome around it. And similarly, we have an OR gate. I'm not the best drawer in the world, but let's draw that a little bit bigger so you can see an OR. Right? OR gate. Something like that. I am not an artist, and I apologize. Similarly, you can invert the outputs of those. We do that by putting a little bubble on it. That means inverted. And this is NAND. Do that to an OR gate, you end up with NOR. Another way, if you're just inverting, this symbol is a buffer. With a circle on it, it's an inverting buffer. We just call that an inverter. Right? Now, NAND gates and NOR gates bubble can also be drawn by, and this is very important to remember, this bubble can move to the other side, and then we just flip the type of gate. So while this is a NOR gate, so is this. And while this is a NAND gate, so is that. So you have two forms of the NOR and NAND. Now these are used as universal gates in all types of logic systems and are therefore really important to remember these forms. Of course, remember the other ones, but remember that these two are interchangeable. And these will come into some of the design steps that we'll get into later. And the idea is that we want to be able to draw a circuit from it. And your book is going to go through some of those examples, and I will go through the design steps. This is the way that I like to do it, and we're going to do this as a fairly complex example to show you how not that difficult it is, as long as you get Demorgans' theorem, or what do they call it, Demorgans' law? Right, Demorgans. I always just say Demorgans. I am sorry if I mix up the specifics on it. So, I'm going to explicitly write the AND because that's useful when you're doing anything with Demorgans. Okay, looking easy so far? Well, it's complicated. We're going to have not A and B knotted, and then we're going to knot the whole thing. Okay, now it's a proper mess. Proper mess. There we go. So is my language apparently today. We're going to use Demorgans. And now there's really two terms in this because we're focusing here on this big knot. It's very difficult to draw a function into a circuit when you have large terms being complemented. So we get rid of that by using Demorgans, which we're going to take this as term 1 and this as term 2. Now, what we can do is we can undo this knot, this inversion, this complement, and change out any of these, right, ands to ors, ors to ands, and invert any of the terms. But this is a term 1, and this is term 2. We're not considering the smaller interior terms yet. We're just looking at these as bulk. So, big knot is undone. Interior terms are flipped. So what that means by A, B, knot, right? This stays the same, but then we complement this complement, which means it's gone. And this AND becomes an OR. This guy stays the same, A bar, B bar, or C, because we're not changing these guys, we're just looking at this whole term. But he now, unfortunately, gets a complement. But, fortunately, we can just do Demorgans again, and we have to look at each of these terms on their own, right? Because this guy is no longer part of what we're going to use for Demorgans, it's just this one. So get rid of the main complement, flip all of these, turn ors to ands. So we have what we're keeping, or A, because it was a bar, or B, oh, see what I did there? Or is, it's not and B, and C bar, because we're flipping it to a complement. Okay, so that is equal to, let me slide this up. Okay, this is a pretty simple term, but we can start looking at some simplifications perhaps. We can pull out that B. And now we have A bar or A C bar. Oh, well, if you watched the last video, if you have, what's the rule? A or not A, B is equal to A or B. Sorry, that's a little crammed, but it'll make sense in just a minute. So our A in this is actually not A, right? And then our A bar is A, and our B is C bar, which means that we have B of not A or C bar. Sometimes, frequently in fact, I will explicitly call out these terms to make sure I don't screw any of them up. Now we have a nice simple term. We have no more complements over large terms. All of our complements are just on the input. So that's really a nice and simple way to do it. Now, as I always say, I like to start at the top level. I have an AND here, right? So I can know that there's going to be an AND gate at the output. And then one of the terms is just a B. And the other one going into the AND gate is A or C. So I have an OR gate. Sorry, A bar, C bar, going into this OR gate. Boom, we have a circuit. We want to do this in universal gates, though, right? So let's remember the circuit, B, A, C, and ORs, and flip to the next page. Okay, we have an AND at the output, B, OR gates over here, A, C. Okay, but these are not universal gates. So the first thing that we can do is this looks like an AND gate, right? So what do we need to do? We can make this a NOR gate just by adding circles at the beginning of it. But that inverts the output. On one side, that's actually pretty easy to deal with, because if I have an inversion here and an inversion here, right, -1 times -1 is 1. So I'm just going to take that OR gate and put an inverter on the output of it. And now I'm taking AB into this OR gate, or sorry, NOR gate into a NAND gate. Those are universal. Well, we don't have another gate up here, so we just have this B that's been inverted, so we have to put another NOT. One way to do that, right, is just throw up an inverting buffer in its place, or you could just write it, the input as B bar, right? So now I've converted to universal gates. There's probably has an official term. I always just call it bubble pushing. And there's other ways to do this, but for now, I think I'll leave it at that, and we'll come back at, let's see, section 5.3 is where this roughly leads us off, and we'll start up there when we pick up class next week. All right.